we're doing circle geometry in mathematics. Okay, so the circle can be divided into many parts. For instance, when I put a line from any point of the circle to another, that line is known as a chord. A chord. So, but when that chord passes through the middle of the circle, it becomes a diameter, meaning that it divides the circle into two equal parts. Now, at the center of the circle, if I put a line from the center of the circle to any point on the circumference of the circle, this is the circumference of the circle. Circumference. So it is total perimeter around the circle. So if I take a line from the middle of the circle to any point of the circumference, that line is known as the radius of the circle. Now, a chord divides the circle into what we know as segments. We have the minor segments, that's the smaller parts, minor segments, and then the larger part, which is known as the major segments. The chord also divides the circle into arcs. We have the minor arc and the major arc. Under this topic, we'll be dealing with so many things that have to do with the circle, so many theorems and laws that we'll be using to solve various questions under circle geometry. So, for instance, let's have the first theorem. Theorem 1. So, a straight line drawn from the center of a circle to bisect a chord which is not a diameter is at right angles to the chord. Now I will have to explain what this means. A straight line drawn from the center of a circle. So we have a circle here, and this is the center of the circle. Now, to bisect a chord, now we have to draw this chord first. Let us know our chord is at the bottom part of the circle, and then we draw a straight line from the center of the circle to touch the chord. So it's bisecting this chord, meaning that it is dividing the chord into two equal parts. So now you can see this straight line is not definitely a diameter. That's the chord is not a diameter, the chord is at the bottom part of the circle. So this straight line that divides it is at right angles to the chord. Now you know that a right angle is actually 90 degrees. So you're having it this way. 90 degrees. So I can put the line here. Definitely you can already see a right angle triangle here. We have 90 degrees, and this is the hypotenuse, the opposite, and the adjacent. So let's consider a very simple example using this theorem. Okay, this is our example. A chord is 12 centimeters long. The radius of the circle is 10 centimeters. Calculate the distance of the midpoint of the chord from the center of the circle. So this is our example. Anytime you want to solve something like this, the first thing you have to do is to draw a diagram that illustrates the information you have been given in the question. So I'll first draw a circle first. Then I will now put the chord. The chord is around here. 12 centimeters long. Okay. So the radius of the circle is 10 centimeters. Remember I told you that the radius of the circle is that line that is drawn from the center of the circle to any point on the circumference. In this case, I'll be drawing my radius from the center to the end part of the chord around here. Okay, so then we'll now ask to calculate the distance of the midpoint of the chord from the center of the circle. This is the midpoint of the chord, and this is the center of the circle. So the line joining it is what we're asked to find. So to make things easier, I can actually name the points on the circle by putting in letters. So let my center be O, let here be A, B, and midpoints should be M for midpoints. Okay, now I am looking for this distance OM. This is what I'm looking for. So to solve this, remember we're given the distance of the radius to be what? 10 centimeters. So the radius of the circle is 10 centimeters and the chord is 12 centimeters. Now we're now asked to find the distance OM. So to find OM, to find OM, we will have to use Pythagoras theorem because we are having a right angled triangle here. So to find the third side, we're going to use Pythagoras theorem. But before, in case you are getting anyway confused, I will have to bring this part for you to understand it better. I'm bringing just this part out in a diagram. So this is what we're going to have. So this place is 10 centimeter. Remember, if from here to here is 12 centimeter, then the distance AM is going to become 12 centimeter divided by 2 centimeters. So that is going to give us 6 centimeters. So meaning that this place is going to be 6 centimeters. So this is M, this is O, and this is A. So we are now finding the third side. So using Pythagoras theorem. Now Pythagoras theorem developed by Pythagoras says that C squared is equals to A squared plus B squared. Or you can say hypotenuse squared, I'm writing that over here, equals opposite square plus adjacent square. I usually like using this one because this is a more simpler formula for you to use. So we are finding this side. So our C square represents the hypotenuse, which is the longest side, and that is 10 centimeters. So I'll write 10 square equals, now A square is what we're looking for, the opposite side. So 10 square equals A square plus B square now represents this side at the bottom. That's 6 centimeters. So 6 square. Okay. Now, I hope you are really following me along. So, A square becomes 10 square minus 6 square. Remember, this one came over to the other side of the equation to become negative. So, A square becomes 10 raised to power 2 is 100. And 6 raised to power 2 gives us 36. So subtracting this, A square becomes 64. So to get A, I will have to take the square root of both sides. So that becomes A equals square root of 64. Finally, the square root of 64 is going to give me what? 8. So A equals 8 centimeter. So that means OM, side OM, therefore OM equals 8 centimeters. If you have perhaps any issue with clarity concerning what happened in this place, let me open it up for you to see. Take the square roots of both sides. Now what happens is that the square roots cancels out the square. So we'll be having something like this. A square equals 64 like this. So the square roots cancel out the square, and what we have here, square root of 64, is what finally gave us 8 centimeters. So with that, I'll be moving to the second theorem. Okay, so theorem 2 is all about the angles of a circle. The angle that an arc of a circle subtends at the center is twice that which is subtends at any point on the remaining part of the circumference. Now, one thing about maths, you might actually think maths should just involve numbers and calculations, but sometimes we have a bit of English in mathematics, and I'm actually here to help you understand this part. For instance, consider this circle. First thing we have to do here, we are going to put the center and then draw 2 lines. That's radius to the circumference of the circle. I'm actually going to draw another line here. Another line, something like this. Now, we have more or so like two sectors here. So what this theorem says is that the angle at this point is twice the angle at this point. Now to say the angle that an arc of a circle subtends at the center is twice that which subtends at any point on the remaining part of the circumference. Now this is the angle that this sector subtends here at the center. So it is twice the angle that it subtends at this point. So if here is x, this place becomes 2x. Given the fact that this is O at the center of the circle. So let's have an example with this theorem. Okay, so our example on the theorem 2 says O is the center of circle WXYZ. If XWZ equals 33 degrees, now this little cap on W means that the angle is on W, that is 33 degrees. And it said find XOZ and XYZ. So we have the circle over here and we have WXYZ. So this is XWZ we are showing here. XWZ, you can see the angle is what? 33 degrees. Now we have to find XOZ and XYZ. Looking at this theorem 2, to find XOZ, XOZ, 2 times 33 degrees. Why? Angle at center is twice of angle at circumference. So that equals 66 degrees. So this point here is actually 66 degrees. Now, for us to find XYZ, that is this place, we are going to have to find the reflex part of XOZ, that is other part of the angle. So to get that, find the reflex of XOZ, that's XOZ reflex is going to equal to 360 degrees minus 66 degrees. As we are going to remove this amount from this place. Why is that? Because it's the sum of angles at a point. So subtracting that is going to give us 360 minus 266 is going to give us 294 degrees. So that is XOZ reflex, the larger side. So using this now, we're going to have to find the other side, that is XYZ. So XYZ, remember from our theorem, we said that this point here is twice this point. Why? Because it's the side that is facing the angle here. You can see they are all facing the same direction. This one and this one facing upwards. So this means that this one is twice the angle of this. So that means XYZ becomes 294 degrees divided by 2. And that's going to give us 147 degrees. So XYZ equals 147 degrees, while XOZ equals 66 what? Degrees. Okay. So theorem 3 states that the angle in a semicircle is a right angle. The angle in a semicircle is a right angle. To prove that this theorem, consider this place AOB. AOB is this angle over here. Now this way or this way is equal to 180 degrees because sum of angles on a straight line. Okay. So since this place is 180 degrees, remember our theorem 2 that states that the angle at the center of the circle is twice the angle at the circumference. So that means AXB is equal to 180 divided by 2. It will give you 90 degrees. What is the reason? Angle at center is twice of angle at circumference. Now, you can remember, any triangle that has 90 degrees as one part of it is definitely a what? The right angled triangle. That is why this theorem states that the angle in a semicircle triangle, the semicircle is a right angle. So whenever you see semicircle, you see any angle in that semicircle, that angle is a right angle. So we have an example on this. So our last example for today, PQ is the diameter of circle PMQN, center O. So if PQM equals 63 degrees, find QNM. Now this is PQ, is the diameter cutting across from this side of the circle, the other part, dividing the circle into two equal parts. And this is the circle PMQN, and this is the center of the circle O. If PQM equals 63 degrees, find QNM. This is QNM. See QNM. So this is the angle I'm looking for, and we have this angle. So using this theorem, we're going to be able to find QNM. The first thing you should notice is that we have a semicircle here. So using this theorem that we just learned, the angles in a semicircle is actually a right angle, meaning that PMQ equals 90 degrees. Angle in a semicircle. You see, this place here to this place actually account for a semicircle. So since we have this angle over here, this is actually 90 degrees. So the next thing is to find this place, QPM. And I'll tell you why it's very necessary for us to find QPM before we can find QNM. This is it. So to find QPM, it becomes 180 degrees minus 90 degrees minus 63 degrees equals QPM. Why? Sum of angles on a triangle. Sum of angles on a triangle is actually 180 degrees. So if I remove 63 and 90 degrees from 180 degrees, what I'll be left with is angle QPM. So that becomes, if I add up this and this, 90 plus 63. 0 plus 3 is 3, and 9 plus 6 is 15. So that's 153 degrees. That becomes QPM equals 180 degrees minus 153 degrees. So QPM equals 27 degrees. So having 27 degrees over here, what is simply left for us is to equate it to this one. That's because there is a reason for that. This is it. Since therefore QNM equals 27 degrees, because QPM equals QNM. Why does QPM equals to QNM? You might want to ask. It is because they are angles in the same sector. That's another theory we'll be studying in the next class. Angles in the same sector. Remember when I began this class, I drew a circle and I put a chord around it, and I told you this place here is minor segment, and this is a major segment. Now, this naturally here, this place here is a sector. This is an arc, and this is a sector around here. That's something like this. This is a sector around here. So this is a minor sector and this is a major sector. Now consider these two angles, MPQ and QNM. Consider these two angles. They are both in the same segment. Then the six segments. Look at this segment here. This is the chord over here. And then look at all the angles here. You see, this is the angles that are facing them. These are the angles that are subtended by this chord. That is why, because this given is 27 degrees, here it becomes 27 degrees. So therefore, QLM equals 27 degrees, while PMQ equals 90 degrees. Thank you for watching. In our next class, we are going to be studying other theorems on simple geometry. Please remember to hit the subscribe button. Thank you. See you next time.